everybody for joining us. Let me just record quickly. Oh, it is recording. All right. Okay, great. Thanks everyone for joining. And thanks so much for Daisy for volunteering on accepting our invitation to be a webinar demonstrator today. And Daisy will be presenting a demonstration on how to handle missing data using mice in R. So Daisy is a PhD candidate in the data science at Hasselt University in Belgium and is based at the Aga Khan University in Kenya. She has a strong background as a statistician. Daisy brings extensive experience in handling real-world routinely collected health data, particularly addressing the challenges of missing data in such contexts. Her doctoral research focuses on developing predictive models for poor birth outcomes using routinely collected maternal and neonatal data. She is passionate about leveraging open source tools, especially R, to promote reproducible, high-quality research in low-resource settings. She routinely applies advanced statistical techniques, including multiple imputation in her data analysis. All right, happy to have you here, Daisy. Over to you.
Thank you, Rolanda, and welcome everyone. So I think Rolanda have introduced me. I'm within the ULIMA data science projects in DSI Africa. And today I'm going to take you through a brief introduction of how to handle missing data using mice in R. So just a brief introduction is that data can come in many forms. Sometimes we have structured data, which is in tabular form. And sometimes we have data that is maybe text, images, or audio. And once you get your data, the first step is to try and visualize your data and then cleaning it. So cleaning data, you clean data so that it is ready for analysis. And during data cleaning, you have to identify the problems that your data has. And then now you go into the processes of cleaning the data. So some of the issues that data usually have is missing values. So especially when you're handling routinely collected data, it has a lot of missing values because maybe these are data from hospital entries. So patients come into the hospital and we have nurses collecting the data. Sometimes this data has missing values. And then also sometimes it has duplicate records, irrelevant values, outliers, or even inconsistent values, among others. And so before analyzing your data and getting insights out of it, you need to begin with cleaning your data. And today we would just want to focus on handling missing data. And so I want us to see this case study just to show the importance of missing data. So suppose you're conducting a study and you want to assess the impact of socioeconomic status on depressive symptoms levels. And then so you go out there and you survey participants on their income, education level, and depressive symptoms. So however, as you collect your data, a significant portion of your participants who have lower incomes do not complete the survey. And this could be because maybe they are busy somewhere looking for money, and so they are not able to, fill in the survey. So you decide to do a complete case analysis of this data. So you can already guess what are some of the biases that can result from this. Remember that most of the people who did not complete the survey are people who have low income. So your analysis, your complete case analysis will have some biases. And one of the bias that will be introduced is selection bias. So if individuals with lower incomes are less likely to complete the survey, the final dataset may disproportionately represent individuals with higher incomes. So this can lead to underestimating the association between low socioeconomic status and higher depression levels, because the data now mostly reflects participants with high incomes and possibly lower depression symptoms. We also have the next bias that will be introduced is attrition bias. So if those with severe depression, for example, are less likely to complete the survey, maybe because they are, disengaged or they are too overwhelmed, then your study will underestimate the prevalence of depression in the population. So your results will be biased because it will show lower depression levels than actually exist. So in both cases, missing data systematically excludes participants with key characteristics, low income, so those with low income and those with higher depression. This leads to biased conclusions and also may skew your findings. So another thing is that for most studies, you usually compute the minimum sample size to obtain a certain power. And so if, let's say, you went to the field, your initial plan was to collect 400 data from 400 participants, and you actually collect data from maybe 450 participants. And then when you come to do your analysis, you find that 100 of the participants have missing data. So at the end of the day, if you do complete case analysis, this is where you include those with missing data, you will find that you now have 350 participants. So your sample size will be below the threshold that you had initially set. And so you have to have a way of handling this missing data to ensure that you maintain the power that you had initially anticipated. So the risk, there are 4 reasons or 3 reasons why missing data, 3 classifications for missing data. And so missing data are classified into three categories. One is you can say that missing data is completely at random, or missing at random, or missing not at random. So we will briefly look at missing data pattern. So these are missing data patterns, and we will briefly look at each and every one, each of them before going now into how to handle missing data. So we say that our data is missing completely at random if data on the variables, if when the probability of missingness does not depend on other variables or the missing variable itself. For example, suppose you're collecting social demographic data on age, and some people skipped the age question. So you are collecting data, social demographic data, and you have a question asking data on age, and people somehow skip this question. And the reason for skipping has nothing to do with their age or other variables that are in the dataset that you are collecting. So then we say that age is missing completely at random. The next one is missing at random. So we say that your data is missing at random when the probability of missingness on a variable is related to other observed variables and not the missing value itself. For example, now using also our previous example, you are collecting data on social demographic characteristics of a population. And we know that women doesn't like reporting their ages. I don't know why. So somehow gender or females do not report their age. So it means that the missingness of age as a variable is dependent on gender. So once you account for gender, then missingness in the age variable doesn't depend on the variable itself. So age is missing because the female gender are less likely to report their age. So in this case, we see that the probability of age being missing is related to another variable, which is gender. But when we account for gender, then the missingness of this variable doesn't depend on the variable itself. Yeah, and then the next one is missing not at random. So these 3 classifications are really important as you decide the method that you are going to use to handle your missing data. So we say that data is missing not at random if the probability of missingness is related to the missing value itself. So, for example, now older people are more likely to skip the age question because they feel uncomfortable sharing their age. So, in this case, age is missing because of age itself. So, I don't want to report my age. So, age will be missing because of my age. I am too old, and I hear you people saying that I'm too old. So, age will be missing because of my age. So, missing not at random. So let us now look at ways of handling missing data, considering that you've understood the different missing data mechanisms, that is missing at random, missing not at random, and missing completely at random. The first method, and which is really common, is complete case analysis. This is where people exclude rows or observations that has any missing data from analysis. So in your analysis, if you have maybe 4 variables and one variable is missing for a certain observation, you exclude that observation. That is complete case analysis. It is useful when missing data is minimal. Maybe you just have one person with missing data. And then also if your data is missing completely at random. This, however, reduces the sample size and might lead to loss of statistical power, just as we have said before. It can also introduce bias if the data is missing not at random or missing at random. The next one is pairwise deletion, and this is common when you are using basic methods like correlation analysis and covariance calculations. So in this case, you use all data, you use all available data for each analysis, and you only exclude the specific pair of variables when a missing value occurs in one of them. So one difference or one major difference with listwise deletion is that with listwise deletion, you exclude an entire observation if any variable used in the analysis has a missing value. But then for pairwise deletion, you only exclude the specific pair of variables when a missing value occurs in one of them. So, and it's, as you can see, it can lead to inconsistent sample sizes across analysis. So if you're comparing, you have, let's say, 10 variables, and you need to do correlation for two variables. So every time you are doing pairwise deletion, it means that at the end of the day, you will be having a varying sample sizes. And then also it might be hard to interpret and can introduce bias if you're doing multivariate analysis. So there is also one common mean, median, or mode imputation. So you simply replace the missing value with the mean of the observed mean, mode, or median of the observed value. So for age, if age is missing, I just find the mean of the age variable and then write or impute that the missing age observations with the mean. So this is useful when data is missing completely at random and the proportion of missing data is really low. So it is simple and most people do this. However, it reduces the variability of your data. And if data is not missing completely at random, then you have bias introduced. It also does not account for relationships between variables. Other methods for handling missing data, and these are listed here, but because of time, I just want us to go directly to multiple imputation. So multiple imputation imputes missing values multiple times. And this creates several different data sets, and then you pull the results to account for uncertainty. So it is useful when data is missing at random and you want to account for uncertainty of the missing data. It is also suitable when you are doing complex analysis. So when you are doing multivariate regression, this is really suitable and you're able to have, you simply impute the data multiple times. So I'll explain it during the practical. And then it is really, when you have a large data set, it can be complex to implement. So I remember running multiple imputations that took like a whole day. So it's just running on your computer for a whole day. And the results depend on the imputation models that you're using. So you really need to be careful with how you're choosing your imputation model. So it also cannot fully handle missing not at random data. So you have to make the correct assumption of missingness, which sometimes can be difficult. So we are going to go directly into how to handle missing data using mice in R. And I hope you people have installed R already. You can use this link here, which you can follow later during your own time. You can follow the link later. It has some vignettes that or demonstrations that can really guide you on how to perform multiple imputation using mice in R. And I think also there are Python modules that does this. So if you're a user of Python, you can check that. So one thing that so let's go directly to that. So do you have any questions to this far?
Sorry, Daisy, just a comment. I managed to receive your presentation, so I copied the link and shared it in the chat, the one that you just shared.
Okay, so let me share our studio.
Are there any questions at this point for Daisy?
Yeah, so if there are no questions, we'll continue. So this is my art studio, and maybe yours could be different, how these tiles are organized. So this first part is where you write your code. And so one thing that I wanted to mention, if you are installing R for the first time, is that you need to install R first, and then run it, and then install R Studio. So that is really important. And then once you install, you have R Studio, when you open, this is what you find in the first place. And you can click File, New, and then you open a new script. So when you click and find a new script, this is where you can start writing your code. And then this other side on my right hand, this is the global environment. So my data sets will be appearing here. And then on this lower right hand side, we have files. I can already open files from this area. And then when I have plots, they appear on this window also. Packages, if you are installing packages, for example, we are installing the mice package, you will click install here, and then inside here you search the package that you want to install, and when you click install, your package will be installed. And then you can also find information about the packages and the functions in R in the helper function. So for example, if you want to find information about mice, you come here, you type a question mark, and if you press enter, you have information about mice here. So it's really helpful. Yeah, and then, yeah, so that is basically what it does. And then here, this is the console where whatever code we write will appear here. If we have a success or a failure in running our code, then they all appear here. So I hope you've installed these packages, the mice package, the Vim, and the lattice package. So in R, when you want to start using packages, you'll need to run the library function. So I'll run the mice, Vim, and lattice. So we'll also need to set seed. So setting seed, so this is just any number. You can put 1, 2, 8, whatever number, but it ensures that you have same random results every time you run your code. So for some functions that involved randomness, if I don't run this seed, it means that tomorrow when I come running my code, I'll get a different result. But if I want to get the same result, then I'll use this seed. So let's run that seed. So we are using the end-harness dataset, which is within mice. And so we just want to begin by viewing this dataset. So once you begin, you receive your data, before you analyze the data, you want to see the data, you want to see the variables, you want to see the distribution of missing data in that dataset. So I've clicked view, and as you can see down here, the code is written down here. And you can already see that there's an error when I was running the library lattice, because I think I'm not using the correct spelling of that package. But then here we can be able to see our data. We have 4 variables. We have the age, the BMI, hypertension, and what was the name of this? So we can already know and use the helper function to show us information about this data set. And so we have variables, age, BMI, hypertensive, which is a yes, no, and then cholesterol. So we have information about that data set. So we can also run a summary of that data, and this is how our data is. For example, we can see that the minimum value of BMI is 20.4, the mean is 26.56, and there are 9 missing values. For hypertension, we have 8 missing values. For cholesterol, we have 10 missing values. And then now we also want to, so the mice package has functions for visualizing missing data, and one of them is md.pattern. So if you run md.pattern on your data set, you have this image. I hope you can see that. I have zoomed it, so I hope sharing. Okay, let me just share it here. So this one visualizes our missing data, and this is really important for you when you're it's important to have a visual representation of your data set, your missing data, to enable you to understand if there are any systemic errors in your missing data. So here you can see there are 27, down right corner there are 27 missing values in total, and the age variable has 0 missing data. The hypertension variable has 8, the BMI has 9, and cholesterol has 10. And then we have 13 rows that are completely observed. And then we have 3 and 3 plus 1, those are 4 that have 1 missing data. So the red ones are missing. It shows here 1 has missing. We have 1 row that has 2 missings, and 7 rows that has 3 missing observations. So this can be complicated if you have many variables, and there are other packages that can help you when you have so many variables. Yeah, so we will go directly into imputing our data sets. And so the basic thing that people usually do when they receive their data and they have not handled missingness is they run their regression analysis directly. So I started here by running a linear regression model where age is predicted from BMI. And let me just run this code. And as you can see, when you run the summary function, it tells you that 9 observations are deleted due to missingness. So something that people don't usually pay attention to when they are running a regression model is that they don't pay attention to the values that are deleted. So here 9 observations are deleted. And if you were aiming for, these are 25. So this data set has 25 observations, right? And if that was the least sample size that was required for you to have 80% power, then if 9 observations are deleted, it means that your power has reduced. It's no longer 80%, and it means that your inferences are not going to be correct, are going to be biased. So I want us to also do mean imputation. So mice can, so when you're doing mean imputation, you don't have to manually go and compute the mean and write a function that will, impute the means. So mice has that functionality, and you specify that with method. So you put in your data sets and you specify the method as mean. You want to do one, so M represents, we can see that in the helper here for mice. M represents the number of imputations, and max fit represents the number of iterations. So how many iterations do you want your imputations to run? So because we are doing mean imputation, we don't have to do more than one imputation because it will repeat the same thing. So let's just run that.
Sorry, Daisy, to interrupt you.
Yeah.
So there's some questions in the Q&A chat. Lionel is asking, how can we follow if you're using the cloud version of RStudio? So I'm not sure.
If you're using?
If you're using the cloud version of RStudio.
Okay, so if you're using the cloud version of RStudio, you can still, I think you can still write these. I have not used the cloud version of RStudio myself, but it shouldn't be hard for you to be able to download the packages and do this. Yeah, unless maybe she wants to talk.
Lionel, I don't know if you would like to unmute yourself.
Okay. Okay. So maybe you'll need to type in the codes because I'm not using the cloud version.
Hello.
Go ahead.
Yes, greetings and thank you for giving the floor. In fact, on the cloud version, because I did not have time to install all the packages before the meeting, but the interface is the same. However, I don't have, I don't know if there's a package that I need to install to follow the command that you are doing, but the interface is quite the same, the cloud version of RStudio. But when I'm typing the same command, the first command, even on the console, they said the package none. So I don't know if there's a small thing that I need to do for the package to be known on the cloud version.
Okay, so I don't know if you have installed mice. Have you installed mice?
No.
Yeah, so you go to packages, yeah, or you can run this code install.packages and then brackets mice. So if you run that, after you run that one, you then run library and then
Okay,
mice.
okay. I think I'm getting now. I'm getting just that line was not visible when you were explaining. So I don't know how I can get all that. If you can paste it maybe in the chat so that I will not disturb you while you are doing. If you can, I don't, yeah. So that I will just run the, I don't know, it's possible.
Yeah,
Because now I'm seeing
please.
that when you are explaining, the thing goes up and I'm not getting.
Okay, let me just explain that. Do I paste it in the chat or the Q&A, Rolanda?
That's fine. Yeah, whichever means is best for you.
Q&A. Let me paste it. So I have just pasted everything up to where we are. Yeah, so I hope you're now okay. So
Yeah, I think
we were here. Yeah.
Yeah.
So we were doing mean imputation, and I just told you that you can do that using mice. So I've seen people struggling to compute the mean, and then you come and write a function that will go and find missing values in your data set and put in the mean there. So you can easily do that with mice with just one line of code. And then now, once you are done with the imputation, you want to get the complete data set with now missing values imputed with the means. And there's this function, the complete function in mice. It shows shows you the complete data set. So if I run that, here you can see our data sets and our variables. You see right now it has no missing values. And if you can see the BMI, for example, it has 26.56 appearing several times. This is the mean that was being imputed, right? So you can just confirm by running the means for the 4 variables. And you see that the mean for BMI is 26.56. So this is it. This is down here. And as you can see in our data set, 26.56 appears so many times because that is the mean. So we now want to fit our regression model where age is predicted by BMI. And we run that. And as you can see right now, our model is not complaining that variables are being dropped, right? But nothing changes actually. If you look at this estimate compared with what we had before, there is no big difference. That is because BMI is normally distributed, and so when you just add in the means, you just add the weight of the means, and there is nothing more that you are doing. So it's basically similar. And then we now the next thing is so I was telling you that BMI is normally distributed, and if you plot a density plot of BMI, you can see it is normally distributed, and so you using the mean doesn't really add any value to your model. And then we now want to impute the missing data using multiple imputation. So when I just ran mice here, remember when we were doing mean imputation, we specified method to be mean, and we specified the m, which is the number of imputations to 1, and also the maximum number of iterations to be 1. But here, I just want us to use the default settings for mice. And when I run that, you can see we have 5 imputed datasets. So I want us to see the default settings in mice. So this is how you see it. You type question mark and then mice, and then run that. When you run that, the helper shows, and we can see here the default settings. So we have MS5, which means we'll have 5 imputations, and we can see we have 1, 2, 3, up to 5, and each one has been repeated 5 times. So that is the number of iterations. You can also find more information about mice in this helper. And also we have examples down there and many more, a lot of information that could help you when you're doing your analysis. We have other things that you could change, adjust, just to ensure that you're having plausible values. So once that is running, we want to now view what is in this the imputations that we've just done. So when we run that, we see this is what we get is of classmates, and it's really important that you know that this is of classmates, because further when you want to do other things, sometimes, for example, when you want to do some regression analysis, sometimes it requires you to have a data frame, but not that this is not a data frame, it's a MIDS, it's a class MIDS. And we are told here that the number of multiple imputations are 5, and the imputation methods used for age, because age did not have any missing values. We saw here that age does not have any missing values. And so BMI, for BMI, we used predictive mean matching for hypertension and also for cholesterol. We used predictive mean matching. This can be changed, and I want you to look at the methods just on the right lower side. So predictive mean matching is just it's a method that we used, but you can also use random forest, you can use logistic regression, you can use proportional odds model. There are very many methods that are available. It will depend on your data type. So if, for example, you're having a continuous variable, then you will want to use predictive mean matching. But then if your variable is, so we can specify, for example, for hypertension, we can specify the imputation method to be logistic regression, because we know that that variable is a binary variable. And then when you want to, so this variable also has your original data. You can see your original data there. And then when you run this one also, it also shows the imputations. So if you run imp2 and imp, you see your imputations. So your imputed data sets. So right now we are having 5 imputed data sets, and we can see them here. So this is the first imputation, the second imputation for every variable up to the 5th imputation. So now we can also extract complete data sets. So I told you that we have 5 imputations, and this complete function, we specify the variable name that the name that variable, the name that you had given your imputed data sets, and you specify that you want the second imputed data set. So if I run that, I'm able to see now the second imputed data set with all missing values imputed. So I hope you notice that we are now having 5 imputed data sets, because we specified our number of imputations. Okay, the default mice function has 5 imputations. So let me copy paste this again, just in case someone wants to run them. Yeah. So if we run the MD pattern again, we see that none is missing, right? Unlike before, when we had several having missing values, right now in our imputed dataset, we have all observations are observed. And now we will want to maybe take now all our 5 imputed datasets, and you can do this either as in the long format or wide format using the complete function. So you feed in your imputations, and you specify whether you want long format or wide format. So I specified here that we'll be taking the long format. I just want us to see how that appears. So as you can see, we have five data sets from number 1 to 25 to 125. So we have 5 data sets all put in one data frame. And then now you want to specify, you can also want to specify the variables that you want to impute, because sometimes you don't want to use all the variables in your data set for the imputation. So what multiple imputation does is that For example, if you are imputing age, it forms regression models using the observed variables, and then it predicts the missing variable. But sometimes you don't want a certain variable to be included in the imputation model. And so you can specify variables that you want to use. You can also increase the number of iterations or the number of imputation. And as I told you, you can also change the method that you are using for imputation. So it's not as simple as it looks. You really need to know what you want, what you are doing, and diagnose your imputations to see if they are working. So what we can do to diagnose our imputations to make sure that we're having plausible values, we can inspect for convergence to see if our model is convergent. And if I run plots our imputations, then you can see on this side, for each variable, we are having a plot. So these line plots should not have a pattern. They should be as random as possible. So when they have a pattern, then it means that your model is not converging. And you need to go back and maybe increase the number of iterations or check if there is a variable that is not behaving so well. So you need to really check the convergence of your model. You can also check the relationship between, so generally one would prefer for the imputed data to be plausible. When I talk about plausible, I mean you want values that could have been observed if they had not been missing. For example, you don't want age to come up as 600. So in order to form an idea about plausibility, one may check the imputations and compare them against the observed values. If we are willing to assume that the data is missing completely at random, then the imputation should have the same distribution as the observed data. But in general, distributions may be different because data may be missing at random, and but we will not be expecting large discrepancies. So we will run a strip plot just to look at the relationship between the observed and the imputed values. So in this plot, where is it? So this should be imp2. Oh my God. I don't know why this one is not running. Yeah, I don't know why this one is not running, but basically it will show you the distribution between the observed and the imputed values, and it should not be so different. Now, we will now want to fit our regression model to our data set. And remember that we have 5 data sets. So when I run the regression model, I'll have five outcomes for each data set. What do you do with 5 models? You want to pull the results. So we have this function, the pull function. It uses Rubin's rules to pull the results. Let us look that up in the help just to get the so the pull function combines the estimates from the M repeated complete data analysis, and it does that in a sequence of steps, and it uses what we call Rubin's rules. So you can go and read about that to understand what happens as the function pulls the results. And so I'll run that. And if I run the summary function, we now have these results for our regression model. And if we compare that with our initial, so we have not lost any data here, and we are not introducing biases by using something like the mean, the median, or the mode. So yeah, so that's it with multiple imputation. One thing that I wanted us also to check is that, to be careful about, is that you need to ensure that you check for convergence. Also check the relationship between the observed and missing values. You can also perform sensitivity analysis. So as I finish there is a certain case study people were using. Let me just share. So there is a published. Next. Okay. So there is a BMJ article that reported the development of a Q-risk tool for cardiovascular risk prediction based on a large general practice research database. And the researchers correctly identified a difficulty with missing data in their database. And then they used multiple imputation to handle the missing data in their analysis. In the published prediction model, however, cardiovascular risk were found to be unrelated to cholesterol, which is not expected, right? And that was surprising. So the authors have now clarified that when they restricted their analysis to individuals with only complete data, that is no missing data, there was a clear association between cholesterol and cardiovascular risk. So furthermore, a similar result was obtained after using a revised improved imputation procedure. So these people used multiple imputation, and it was surprising that they found no relationship between cholesterol and cardiovascular risk, which we all know is not true, right? But then when they went back and used the correct imputation procedure and improved imputation procedure, they found now a result that is expected. So you really need to be careful when you are using multiple imputation. Ensure that you specify your model correctly. Otherwise, you will find things that are not expected. Thank you. Do you have any questions?
Thanks, Daisy. There's one question in the chat. So not the Q&A one, there's a question now in the chat. I can read it for you. Mugumi is asking, sorry Mugumi if I'm mispronouncing your name. How do you choose the number of imputations you want to do? Yeah, you used 5. Is this always the case?
So 5 is the default that is in the mice package. But then sometimes when you go to look at the convergence of your model, you find that it's not converging. So one of the things that you could do when your model is not converging is to try more imputations. So there is no rule of thumb, but people use 10. Most people use, when you read articles that are published, people have used 10 imputations. So you basically need to go during the diagnostic stage. It's when you decide to maybe extend the number of imputations, extend the number of iterations. Yeah.
Any other questions? Please feel free to unmute yourself. Raise your hand.
Yeah, so you can find vignettes online. You are using the link that Rolanda posted. It has 6 modules that you can follow, and it will really guide you on how to do the diagnostics, how to specify, the variables that you want to use, how to specify the different imputation methods for the different variables. So it's not as simple as it looks. So you need to really be careful. Yeah, but again, we've seen the possible side effects of not handling missing data. And also, so you need to be careful with what you're doing.
So Daisy, have there been cases where, for example, they do the imputations for missing data, but years later they might have that actual or close enough data set? And if they compare the two where the imputation were done with the data set that had very many missing values plus the one that now is a bit more complete, does it compare well? Are there any instances of that?
Yeah, they compare well. So what people have done you have a full data set. You have maybe a data set that you have collected everything, and you intentionally remove some variables, and then you try imputing. So when you try imputing and compare the results, they are really similar. That is when you've specified your imputation model correctly.
Okay.
Yeah.
So there's a hand from Lionel. Lionel, please go ahead.
Okay, thank you. Thank you, Daisy, for the presentation. It was very nice and understandable. And I have a question. What guides you at times when you want to choose the approach to feed in the missing data? Because we know if it is, according to your classification, if it is missing data not at random, and the other one, but during practicals or on the field, most of the time, we don't even know why. So it is we are most on the type of missing completely at random. So we don't know what influences people not to fill a data. So I wish to know what guides you at that moment, because if we don't want to do the imputation because we have less resources, we want to maintain that data, what guides you on the choice of the approaches among the different machine learning approaches that exist or many other statistical approaches? What guides you in such cases? Because we cannot choose because it's completely random.
Yeah, so when you don't know the reason for missingness, you can take the missingness at random assumption, and that means that you're using mice, but then you'll need to do a sensitivity analysis. So you need to discuss with your team to see, for example, I was doing a study where we were looking at the changes in hospital admissions after a vaccine was introduced, and we used mice to impute our missing data. But then because we didn't know some of the reasons why our data was missing, we did sensitivity analysis, and we went to run the same analysis, or we went to look for changes in admissions for those who were admitted due to surgical burns, right? So we just wanted to see that there is no, if we would have seen an increasing trend in the admissions due to surgical burns, and had found the same trend in our initial population, that it means that the increase in admissions is not, it's not due to the vaccine, it's because there's an increase in the number of people being admitted to hospital. So you'll need to run your model in a different population, but closely related, and then see if your trends or if your findings are changing. For example, again, I'm looking at children who are low birth weight, right? I can have one subset where I'm looking at children who are extremely low birth weight and those children who are low birth weight. If the trends are similar, then my imputation model is correct. If they are not similar, then it means that my assumptions are not correct. But you can go and search that, go and read further about sensitivity analysis and how you can use it when you are not sure about your missingness assumptions.
Daisy, there's another question before we come to the ones in the chat. There's a question from in the Q&A. He's asking, so for example, if your data set you collected a field for sex, male or female, will you have to convert the fields to numbers before you start the imputation?
What is that question? Okay.
So it's in the Q&A field.
Okay. Okay, would you repeat that? I can't see that here. Would you read again?
Sure. So Sebastian is asking, for example, in your data set, you collected a field for sex, male or female. Will you have to convert the fields to numbers before you start the imputation?
No. You don't have to convert to numbers. So if it's male or female, it will remain as male and female, but you'll just need to adjust the imputation method to logistic regression because that is a binary variable. Yeah. And then
Great.
there's also
Then-
someone asking, I
Yes,
think your
in the chat.
presentation is for cross-sectional data sets. What about the missingness for repeated measures? So if you go read the publications for mice, you can also see how this can be applied in longitudinal data sets. Yeah, so it's you can also apply this for longitudinal data sets.
Oh, great. Are there any other questions? If not, I'm going to thank Daisy. Thanks, Daisy, so much. This was really informative. You presented so nicely. I think everybody could actually follow, even if this is not your field of expertise. We will be able to share the recording, and Daisy, you'll let me know if we can share the slides along with the recording, right?
Okay.
And then
Yeah,
we'll be
you can
able to
share.
do that. All right, great.
You can share.
All right, if there's any person with any last minute remarks? Oh, they're thanking you, Daisy, on the chat. Very useful. I agree.
Thank you, everyone.
All right, thanks so much, everyone, and also for the big group that we had attending today. And we will see you next month for Shahid, who will give us also a tools for data science webinar. Thanks so much, everyone. Have a good day further. Bye.
Bye.